Okay, so first of all, what is it? So I've used this term calculus many times before, and we're just going over it. So it's looking at how things change through time. So it's a very, very simple example. If you think back to the very first lecture that I gave, where there was the bus and the speed equals distance over time. Okay, it's basically how does that speed change through time? Okay, so is the speed of the bus constant or is it changing? Okay, and a changing speed is an acceleration, right? If you change the speed, if you increase it, you accelerate up. If you slow the speed down, then you decelerate, so you have a negative acceleration. And that's all calculus is doing, really. It's basically manipulating equations, doing things to them to describe how a certain parameter is changing through time. Okay? And we'll go through this step by step and this is in, if you've got the blue textbook, this is in chapters 9 and 10. I haven't posted any Khan Academy stuff up yet. I will try and do that this evening. I have to fix my bike close. I wasn't expecting that to be black. Okay, so differential calculus. There are two types of calculus, differential calculus and integral calculus. They are basically two sides of the same coin. One is working out the rate of change of something, okay, and we'll go through simple rules for this, so how that works, and that'll form part of today's and tomorrow's lecture and maybe spill over into the next one. And then the next part is integral calculus, which you can think of it as just the opposite of differential calculus. So if you know the acceleration through time, okay, which is like weird, but I mean, if you know what the acceleration was, you could work out what the speed was. Or if you know what the speed of something is through time, if you were measuring the speed of a car through time, rather than kind of just looking at the mileometer, you could then work out just from the speed how far you've gone. Okay, so it's okay, and you can work out how far you've gone over some interval of time, or the complete all time. And that is commonly called integration. And these two terms, differentiation and integration, are really fundamental to the physical sciences. Okay, so Joseph Leibniz and Isaac Newton figured out calculus, and that allowed kind of modern science to develop. So this is a really important concept that kind of permeates almost all aspects of science. So it's a good way of telling something's a real science or not. So if it doesn't use calculus, it's not a real science. Okay, so geography, for example. Okay, so this is a very, very simple example of differentiation. So we might have a graph that's telling us, like, through time. Okay, we might be recording the velocity of something. Okay, so how fast it's going. Okay, so at time 0, with, stationary, nothing's happening. And as we progress through time, the velocity increases. Okay? So, what is, in this case, we've got velocity up there on the vertical axis and time along the horizontal axis. I'm going to top hat it. What is the gradient of this graph represents? So you should have a thing. So you write down on your phone what the gradient of that graph represents. God, you guys are slow. 100%. Oh, God. Awesome. Okay, so this is essentially the processes that we're going to go through. If you start off with a graph of displacement against time, so that'd be like how far you've gone per time. Okay. If you were to differentiate that, the gradient of that graph would be the velocity. Yeah. So if this graph was if we were plotting distance. in meters, okay? We start off where we begin, okay? And then over time, we might move further away from where we started, okay? And anywhere on this line here, okay, the gradient of that will be meters divided by time, meters per second, so it would be velocity, okay? And then if we differentiated that graph again, we would then get the acceleration, okay? And if we were to wanted to work backwards, we just go backwards and we do integration back the other way, okay? So that's just to kind of give you a bit of a heads up. That's basically that's what we're going to be doing, okay? Okay, so rates of change. Okay, so the problem with if we have on that first graph there, we had a nice straight line. Okay, and we wanted to work out the gradient at some point. We looked at the change in y, so that's delta y. So big delta, that's a Greek letter D for change. I don't know why we use delta, but anyway. Delta y, and for that same change in y, we can look at a delta x. Yeah? Pretty good times. We divide delta y by delta x, delta y divided by delta x, and that gives us the gradient. Okay, we should be really happy with doing that. That's super straightforward. Now, imagine instead of a straight line, we had a nice curvy line. And I think we can move on. Okay, these things are really common. Oh no. Yeah, imagine we had like a curvy line. Okay, you can see what happens now if we have a curvy line on here. Let's have a curvy line. Okay. And we want to know the gradient at some point along that graph. Okay? If we did the same thing, okay, we would not be measuring the gradient at this point. We'd be measuring the average gradient over some distance there. So I think that's what we get there, right? So what we want to do is we want to make this interval really, really small. Okay? So if we make it really, really small, then we're able to get close to that point there, right? Okay, but what happens as we get really, 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 really small? Okay, this number approaches 0 because we're having a really, really small change in the x-axis. Okay, so what happens when you divide something by 0? Yeah, bad times. Okay, so if you divide a number by 0, just try it on your calculator. It does not work. Okay, so we can't. So this is the problem of calculus. So we want to make this interval here really, really, really small, but we can't. Okay, so we have to use kind of mathematics to solve these problems for us. So yeah, this is what we want to do. Okay, let's actually do just a quick worked example of what we think we're going to get as an answer. So what I want you to do is, can you sketch out this graph of y equals x squared? Okay, just a simple y equals x squared. And remember, of course, that axes have negativenesses. Yeah? So draw a nice cross like that, make that y, make that x. And just trying to sketch out what you think that would be. So these numbers here, so this is the x coordinate and this is the y coordinate of some points that we're going to work out on that line. Okay? I want to wander around and see how you do it. Just a shitty one. Yeah, that's What's 2 squared? 4. Yeah, okay, so is it a straight line? What's 3 do to the next one? Do 3 squared. What happens to the negative values?
Yeah.
So hopefully, just quickly go through. See, if we look at, if just ignore the numbers on there, And we're going to draw a graph of y equals x squared. Okay? So we can think about what happens as we just move across the x-axis here. So when x is 0, 0 times 0 is, yeah, I think that's, you get the A points in that one. Okay? And then we could say 1 and minus 1. What's 1 times 1? What's 1 squared? Yeah, technically it's a trick question there, but we'll say that's 1 there. We'll have minus 1 down here, so that's the point. What about minus 1 squared? We could top hat it if you're not being very confident.
1.
Okay, so yeah, minus times a minus is a positive, so that is also plus 1. Okay, let's go 2 up, 2 and minus 2, so 2 times 2 is 4. Okay, excellent. I do some work to say 2, 3, 4. That's 4 up there. That'll be up here and here. Okay, so you can kind of see that as we move out to maybe 3 and minus 3, this is going to go up to something like 9. So it's 9 up here. It's going to be something like that. Okay, so we get a graph that is like a big smiley face. Okay, so it's a parabola. So this is this is a quadratic. Okay. Yes. Oh no, not so happy with that. So all we're doing is just plotting this here graph here. So which is taking x equals 0, which is y equals 0, x equals 1, y equals 1. Just plot it upwards. Okay. Now, rather than do what it says in here, I want you to think about in a different colour. You haven't got colours, have you? Or a dotted line or something like that. I want you to plot what you think the gradient of this graph is. So I want you to plot, instead of y, I also want you to plot, let's call it dy dx. So this is basically for the terminology here is if we've got a big delta y over a big delta x, that's some defined difference. So if you actually have basically a gap between the two places where you're working out the change in y or the change in x. But if we use a lowercase d, this is basically symbology in calculus to mean an infinitely small change in y or an infinitely small change in x. So it's basically asking for the instantaneous gradient at that point. Okay? So we can start to think about what it's going to look like. So what is the sign of the gradient over here? Is it a positive or a negative gradient? Yeah, we've got a nice positive gradient here. Over here, you can see it's a negative gradient. Okay? Now, what's the gradient at 0? Yeah, because at 0 here, you can see that it's horizontal. So exactly at 0, it's going to have a gradient of, thingy, 0. Oh, damn it. Okay, so we're going to have something that looks like that. Okay, imagine this is in a different colour. You could do black. Okay, so now we've got basically another graph that explains how the gradient changes across x. Okay, so what we're going to do for the rest of the lecture is figure out how we mathematically go from this curve, okay, to this curve. How we can work out the gradient at any point along the x-axis. Okay, for an equation for a graph that has some kind of like curviness to it. Okay, that is our goal. Let's see how far we get on doing that. Okay, so So this example is basically how it starts off with these, what we saw, basically where we're looking at these big changes, these big deltas. Okay, so if we start off with our man here, so we've got 2 points on a graph like this, so we've got, we're looking at the gradient between this point here and this point here, right? What is that gradient? Okay, and hopefully you can see that how we go across 1, so x changes by 1, yeah, happy? Whereas y changes by 3. So our gradient is 3. 3 divided by 1, okay? And you could do the same thing for this graph here. So we could make a graph of 2x squared, okay, which would be even steeper, okay? And we could do the same thing looking between gradients 3. Okay, so this is what this is kind of doing. Okay, and as you can see, as we make this distance here smaller and smaller and smaller, our gradient changes, yeah, and gets lower in this case. Okay, so we want to work out what this value is tending towards, because we can never work out exactly what it is by making this interval smaller, because as soon as we make it 0, okay, we end up dividing by 0 and our life falls apart. Okay? I think there's so this is an example of this. So this is a graph of y equals 5x squared. So you can see the scale here is kind of massively, I can use the old, okay. So you see the scale is massively different than this scale here. So this is a really steep guy that's coming in. Okay, and you can see if we wanted to work out the gradient between 1 and 5, which is here, and 220 up there, okay, we would get some value, and that we get a gradient of 15. Okay, so we've got, this would be our x0. Okay, our delta x is 1, so up to 2 here. So this is our initial x value plus some small change in x, in this case a change of 1, takes us to 2. Okay, so for each of these basically values of x, for x0 and for x0 plus some small increment, we can use that equation of the line, y equals 5x squared, to work out what the value of y is at that point. Okay, so we do that for this one here. So we take 1, we plug it into that equation, okay, which is here, so 1, yeah, so we take 5 times x squared is 5, so x squared is 1. And then we take this value here, x plus a little bit, and then we plug it into that equation up there as well. Okay, in this case we take 2, so 2 squared is 4, 4 times 5 is 20. Okay. Then the difference between these two is our delta y. Okay, delta y is 15. Then we get a gradient dividing our delta y. We're going to go through this this approach of the limit. Okay, so basically what we're asking us to do is to work out what this gradient is as this value tends towards 0. Okay? So we're going to go through examples of this. So this is basically looking at this equation here, this top one up here, is, so f is the function of x. So in this case, our function of x, you can think of it as y. Okay, so in this case, we've got an equation that y is equal to, what do you write, 5x squared. So f of x is basically the maths that we're applying to the variable, the variable applying to x. Okay, so you can think of that as basically equal to y. Okay, which is in this case equal to 5x squared. Okay, so that's what f kind of means. Okay, and then the other bit of terminology here is this little dash that's after the f. Okay, you can see here there's no dash, and here there is a dash. And that little dash, all that means is the gradient. Okay, so what this equation is the instructions to work out the gradient of the function, or basically how y changes with x. You basically do this thing here. So calculus has a number of kind of like a number of kind of terminologies. So if we have an equation, y equals, say, x cubed plus x plus 3, something like that, okay? Some equation with lots of x's in it, maybe just one x. Okay? You could think of this as a function of x, okay? So you could say that that is a function of x, okay? It's just mathematicians write it like that. God knows why. So if we wanted to work out the gradient of this function, or work out an equation that describes how that gradient changes through time, some terminology for that would be f dash of x. Okay, we could write that, and then we could work out some equation that describes how the gradient changes through time. In this case, we would be describing this line. Okay, or sometimes you might have y dash. So that's just because this term y and f of x are kind of interchangeable. Okay, and sometimes we have this. We write dy dx. Okay, so what is the equation? This would then equal some equation. Okay, this is just saying what is the instantaneous change in y for an instantaneous change in x. Okay, all of these things mean the same thing. Okay, so if you see them kind of written down, they all mean the same thing. Okay, so if we go back to what we're showing over here, all this equation is doing is saying if we work out the function of x when we've added a little bit onto x, and the function of x without adding anything onto it, that's just working out this distance here. Yeah? This value here would be the function of x with a little bit added onto it, and this bit here will be just the function of x that we're kind of starting out at. Okay? So all of this is doing is then divided by the difference in, the small difference in x that we're looking to measure across. All that's doing is working out the gradient across this average line here. Okay? So what we want to do is what happens to this equation when we make these very, very small. Okay? So we've already discussed what I've told you in what is the discussion. But obviously, if you just make this number small as it is, if you make that 0, you get something divided by 0, which is 0. Right? But we're just going to go through some examples of what happens to that actual equation when we use real equations in that case there. Okay, so this is an example. If we just, our function of x, f of x equals y, f of x equals x squared. So that's the same as this example here, y equals x squared. Okay? Okay, so if we take this kind of general limit theorem kind of equation up there, what we've got to put some stuff into that equation. Okay, so we've got, first of all, we've got the function of x plus a little bit. Okay? And we've got a function of x at any point, okay? But without a little bit added, divided by the small change in x. Okay? So if we then apply our actual equation for the line that we're looking for to these values here, so you can see that that's happening in this. I'll use the crazy little pointer here. Yeah, this guy. So you can see here that this the function of x for x squared is x squared. Yeah? And if we basically then substitute all of this, x plus a little bit, into this equation here for x, we just get this here. So all we've got is we've got x plus our little bit of x all squared. Okay? So all I've done is I've substituted this term here into that equation, then put it into here. Okay? And then the delta x at the bottom stays as it is. Okay? Now, if we then take that equation and then multiply out the top of that thingy there, this is the same as writing, what have we got? We've got x plus delta x squared. That's the same as writing x plus delta x times x plus delta x. Okay, this should look familiar to you from the quadratic equation shenanigans. Yeah? So actually when we multiply that out, we multiply that by that, that by that, that by that, and that by that. Yeah? And that's what we get over here. So we have x squared plus 2 delta x plus delta x all squared. Okay? And that, excuse me. So that bit there is just this bracket here multiplied out. Okay? So we can then see what that gives us in terms of this whole equation at the top here. So we've got this minus x as well. Okay, so that minus x, got x minus x, they cancel out. Okay? And that leaves us with a 2x delta x plus delta x squared. Okay? And that's what we've got here. Now, if we now do, we've got a delta x on the bottom, delta x on top, so that cancels out, and one of those cancels out. So we then simplify that further to this equation at the bottom. So the gradient of the function of x is equal to 2x plus delta x when delta x goes to 0. Okay? Now you can see in this equation now, when delta x goes to 0, this 2x plus 0 is just 2x. Okay? So in this case, the gradient is just 2x. Okay? And we can see what that looks like on this graph over here. If we just plot up, I've drawn it wrong. Okay, so we want to be plotting f of x equals 2x. Okay? On this graph here, we'll do that in black. So at 0, del f dash x is 2x, when x is 0 is, what's 2 times 0?
0.
0, yeah, awesome. Okay, what's 1 times 2?
2.
So 1 times 2 would be 2 here. 2 times 2 is 4. Okay, 3 times is would be something like 6. Okay, so we've got a line that looks something like that. Okay? So what we've done here is using this limit theorem, we've actually manipulated this equation which doesn't work, the one at the top. It's got this delta x in it that when it goes to 0 that kind of screws us over. But actually if we manipulate it using devious mathematical shenanigans, we can get an equation that describes the gradient for every value of x. Okay? So we'll do another example. Okay, so this time, I want you to think about what we do for if the function was 1 over x. Okay, slightly more complex example. So I want you to think about write down. I think we have to. Does that actually show up? Can you guys see that? not so much. I did this at home and then kind of photographed it, emailed it myself. So what I've done here is I've just written out that f dash limit thing. Right? Okay, so we've got, in this case we've got f of x is equal to 1 over x. And what I want to know is what f dash x is equal to, which is also equal to dy dx is equal to, I know you can say that equals to y as well, is equal to what? I don't know. Right? So in this case we've got this kind of like crazy ass example here. So we need to think about f dash of x is equal to this thing limit when delta x goes to 0. Okay? So we're going to get an equation and we're going to make delta x go to 0. And it's just f of x plus delta x minus f of x all over delta x. Okay? So we can then start to substitute in our equation-y things over here, right? So this guy here, it's very easy. That's going to be 1 over x. Yeah? Minus, and this is going to be 1 over x plus delta x. Yeah? So all I've done is just got this, substituted this function into this kind of like term here. Okay? And all of that is going to be over delta x. Now all you have to do now is rearrange that and manipulate it to try and get rid of some of the big delta x's. Off you go. No, I think, yeah, so this is the kind of thing that we're just going to need some practice with. Right? So for those that you can see, that's all I've done here. So what we've got here, we've got two, we just think about the top term. So just think about this, let's get some multicolours going on here. Just think about what we need to do to simplify this. Okay, we've got a top bit of the equation here, which is two fractions. Okay, we want to combine those fractions somehow. Right? If you've got two fractions, a fifth and a seventh, right? You want to add those two together, or take them away from each other. You have to make the bottom the same. Yeah? Okay, so the way that we can do that is we can take this one here, and we can times the top and the bottom by something. Okay, so if we times the top by 7 and the bottom by 7, that fraction would still be the same thing, right? Okay? So we're not going to use 7, because that would be just retarded, right? So if we use x, so 1x over x times this thing here, yep. And on this side, so that's the same. Just gonna do that in colour so you can like see the different shenanigans going on. And on this side here, I want to make it the same thing. So I'm just going to times the bottom here by x plus delta x, and the top by x plus delta x. Okay. So now, add these things together. Oh, I'm just drawing this. Okay, so now we've got two things where the thing is at the bottom are the same. Okay, so I can just start to combine those things together. So that then becomes still over delta x at the bottom. Okay, and we've got x plus the amount there delta x. Okay. But now this top term is going to be x minus, and then 1 times that is just going to be x plus delta x. Following? Pretty, you okay? Okay, so what we can do now is think about, can we actually think about simplifying this term here? Okay, and the obvious thing to think about is we've got something here that we might think about trying to multiply out. Okay, so we could times x by x and x by delta x. Yeah. And this thing at the top here, okay, is just, well, I mean, if you've got brackets there or not, we've got x minus x plus. We can just get rid of those brackets essentially. Okay, so the first thing we're going to do is just get rid of those brackets. So we've got x on the top minus x. Okay, we've also got minus plus delta x. Okay, so that becomes minus. Yep. Okay. X minus x. 0. Get rid of those. Awesome. You guys saw me get rid of those over there. That took away and then magic trick thingy. And then the bottom here, or at the intermediate level, we've got x squared times x, and then plus x delta x. Yeah? All over delta x. Yeah? And that's what we've got on the next bit. So what we've got here is, you can think of this as, we've got a number divided by a number and then divided by sort of what. So this and that guy kind of cancel out. But they don't kind of cancel out, they actually do cancel out. So that then gives us this equation, which would be, so minus something divided by itself is just minus 1. Okay, so minus 1 over x squared plus x delta x. Okay? So what happens to this term now when this delta x becomes very, very small is that all of this term becomes 0. X times 0 would be 0. So when this goes limit of delta x, that's a delta, that's an x, goes to 0, this then becomes minus 1 over x squared. Okay? And that is the graph of the gradient of 1 over x. Okay? So if you think about what that actually means, we've got, say, y and x. Think about what the graph of 1 over x looks like. What's 1 over x at 0? When x is 0, what's 1 over x?
0.
It's actually infinity. Okay, you divide 1 by a very, very small number, it's very, very, very large. Yeah? And therefore you divide 1 by 0, you actually get an infinite result. Okay? What about, so this is quite hard to get, so if we start out, that's 0, 1, 2, 4. Okay? What's 1 over x when x equals 1? So I've got 1 over x. What if I put a 1 in there? Be 1. So 1. Okay, what about if I put a 2 in there? What's 1 divided by 2?
0.5.
Yeah, so that's going to be kind of like here. It's going to get smaller like this. Okay, so we're going to get a graph that looks like that. Yeah. And on this side, when we go to negative, we're going to get the exact opposite. Looks like that. So that's the graph. So if we now think about what the gradient of that's going to look like, that's going to be this equation here. So if we go to 1 here, so if we put 1 into that there, what's the gradient? Minus 1 divided by 1 squared. What's 1 squared? 1. What's minus 1 divided by 1?
-1.
Yeah. So that's going to be right there. What about 2? We make that 2. What's minus 1 divided by 2 squared? What's 2 squared? So it's going to be minus a quarter.
Oh.
Right, so that's going to be kind of up here. Okay, and you can kind of see that that's going to carry on getting, it's almost going to get to, or not. another one up there, looks like that. Okay, and you can kind of see that that makes sense. Okay, so in this portion of the graph, we've got a very, very steep negative gradient. Yeah? And that's what our equation is predicting. It's being a very, very big negative value for the gradient. Yeah? Whereas out here, okay, we've still got a negative gradient, okay, but it's quite a small negative gradient. And that's what we're predicting with our equation. Okay? So those two examples are basically two examples where we've taken a function, either x squared or 1 over x, and we've done this kind of limit theorem thing, where all we're doing is we're saying we're basically working out if we can work out the difference in this term at the top is basically the difference in y for a small change in x. Okay, so it's just working out if we had some curve like that for a small change in x, delta x. Okay, this here is the function of x, and this is the function of x plus delta x. Okay, so we're working out that difference, which is delta y, and this difference is delta x. So we're working out that gradient, but making this progressively smaller. Okay, so we've done that for two simple equations. So x squared and 1 over x. And tomorrow, it is tomorrow, right? Okay, tomorrow we'll go through and work out if we can do that for everything. Everything. Okay? Because once you've worked out you can do it for everything, oh, by the way, you can do it for everything. Okay? Then there are basically a bunch of simple rules that you can just remember. Okay? And you don't have to go through all this kind of like shenanigans. Okay? So I'll leave it at that. I don't think I've posted this working on Learn. It's another thing I'll try and do. So you can kind of go through that and enjoy yourselves doing that. But do, yeah, I'll try and do this like immediately now. I'll put these two examples, or this one work example and the one for x squared. Do try and work through those this evening, just to go over and make sure you can kind of do them. And tell the other guys that they missed out on the most amazing lecture ever. That would be super awesome.